Okay, and hi, welcome back. This is 9.8. In the last section, we kind of were able to connect functions in general to polynomials. So sine of x is approximately something like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And what we're eventually going to show is that if you take a sequence of these polynomials, that they will converge to sine of x. And what we want to do right now is study those limits of the sequences, the actual infinitely long polynomial thing that we'll get from taking that sequence, taking the limit of that sequence. So eventually we'll show that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, on and on and on and on. Okay, so in this section what we're going to do is just kind of focus on these things and look at their characteristics. We'll sort of find an interval of convergence because some of these sequences of polynomials will not converge for particular x values. Okay, it turns out for sine of x, you can put any x you want in there, it's going to converge. But there's going to be other ones where they're kind of not going to work outside of a certain interval. And so we need to use the convergence tests that we developed in sections 9.1 to determine the convergence of divergence. Okay, so in general we will call these things right here at first power series. So in this section we're not even thinking about the connection between the power series and the actual function that they represent. Okay, so first let us define those things, and it's basically just your normal everyday series, except now we have variables. Okay, so power series, the sum of a sub n times x to the n from n equals 0 to infinity, or it could be x minus c if it's shifted around. So you'll get a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus dot dot dot, on and on and on, right? Okay, so this is a power series centered at 0. I apologize for my poor spelling. Okay, so anyways, power series, what the heck was I thinking? I totally lost my train of thought. I apologize. I saw that S in front of centered and I was just like, wow. Okay, so anyways, this is a power series centered at c equals 0, right? Oh, so before, the issue that we looked at in 9.2 to 9.6, I would say, would be things like maybe 3 to the n all over n factorial or something like this, from n equals 0 to infinity. Okay, and that would be 3 to the 0 is 1, all over 0 factorial is 1, plus 3 all over 1, plus 3 squared all over 2 factorial, plus 3 cubed all over 3 factorial, and on and on and on and on. Right? That's what we were doing before. What I'm saying now is that we're going to put a variable in there. And basically, it's like your progression back in elementary school. You started with numbers and arithmetic, and then you went to algebra. Same idea here. Now instead of like 3, we'll say, let's make this variable, right? So let's call, instead of 3, let's use an x instead, all over n factorial, and then we'll have this again. It'll be an infinitely long. Now polynomial now, but it's kind of the same thing. X to the 0 over 1 plus x to the 1 over 1 plus x squared over 2 factorial plus, and this is a series. Okay, this is a power series. And we want to work with this, in particular figuring out where it's convergent, which will mean where is it useful. if it's convergent, then we can use it to do approximations of the polynomial, or of the functions that we're representing and all that jazz. Okay, so convergence is a real big issue here. So that's what we'll spend the majority of this section working on, determining the radius and interval of convergence. Okay, so given a power series, we can call it big P of x, I guess, equals the series a sub n times x minus, and we'll make it more general by including shifted versions with a different center, like from n equals 0 to infinity. We basically wish to know where it's going to converge. We wish to know kind of an interval, or we wish to know the x values for which it converges. So there's going to end up being only three cases. The first case is when it basically diverges everywhere. Okay, if it diverges everywhere, it will actually converge at the center, because when you put it in the center, it's all going to just be 0. So if you put like C in for x into this formula right here, you're going to get 0 plus 0 plus 0, which is convergent to 0. So the first case, it's divergent everywhere, or if you rather, the series converges only at the center. Okay, the second case, you'll have some interval, so I'm just going to call that r. The radius is some number. So in this case, the series converges, and this is absolute convergent, by the way, but the series converges in the interval from C minus R to C plus R, and then diverges for negative infinity to C minus R union with C plus R to infinity. In other words, it diverges outside of that interval, but we have to be careful about the endpoints, and there's going to be a we'll have to investigate that a little more closely here later. Okay. Then thirdly, the case where it basically converges everywhere, and you always hope for this case, but it's not going to always be the case, and it'll converge everywhere for functions like sine of x and e to the x, but not usually. Okay. So anyways, the series converges for all values of x. Okay, so in order to determine these intervals of convergence, we're going to use the ratio test. We'll call it the workhorse, which means it's doing all the heavy lifting and all the heavy pulling. So let's dive in here and take a look at some examples. Okay. So first one, n factorial times x to the n from n equals 0 to infinity. And you can almost see this is probably going to be divergent for a lot of x values. Let's see what happens. So we go to the ratio test. Remember, the ratio test, basically you're looking at this r value, which is the limit of the absolute value of the ratio between a sub n plus 1 and a sub n. And you'll determine the convergence divergence based on the r value. So if r is less than 1, then it's absolutely convergent. Okay, so we'll want to know the values of r that are less than 1, and that usually produces an interval of some type. Okay, so let's dive into this problem and take a look. So the R value in this case will be the limit of the absolute value. A sub n plus 1 will be n plus 1 factorial times x to the n plus 1, and then divided by a sub n, which will be n factorial times x to the n. Okay. Then this will be the limit as, and we're taking it always n to infinity. This will be then n plus 1 factorial, you can rewrite as n plus 1 times n factorial, okay, all over n factorial, and then times x to the n plus 1 over x to the n is x to the n plus 1 minus n, which is just x. Okay. This absolute value part of this part right here, the x, you can factor that out because that's technically just a constant. Okay, so let me show you, in general I won't write it all out, but let me show you how it kind of works. So we have the limit as n goes to infinity. This first part, the n factorials will cancel, so you just have n plus 1. And then you have times x, right? Using the absolute, the rules of absolute values, the fact that the absolute value of a product is the product of the absolute values, we could rewrite this as the absolute value of n plus 1 times the absolute value of x, and then factor the absolute value of x out because it's really not dependent on the limit, right? So you have absolute value of x times the limit as n goes to infinity of absolute value of n plus 1, or you could just write n plus 1 because the values of n will be positive, okay? Okay, so for any value of x except 0, this is going to go to infinity. The only value that will actually equal 0, in other words, the only value where the r value will be less than 1, will be when x is equal to 0. Okay, in other words, so always remember the second criteria. Basically, if r is greater than 1 or r is infinity, then it's divergent. So what this says is that basically for all values of x except the x equals 0, the series will diverge. Okay. And then in that case, your r will equal 0. Okay, the radius is 0. So the smallest radius possible. Okay, let's look at another one. The sum 3 times x minus 2 to the n from n equals 0 to infinity, right? So in this case, we have an r value equals the limit of the absolute value of 3 times x minus 2. This is a sub n plus 1, all over a sub n. This thing you can simplify. So it's going to be the limit of the absolute value. The 3's totally divide out. X minus 2 to the n plus 1 minus n then is just x minus 2. Okay. And then because the limit is in terms of n is going to infinity, this is basically just the limit of a constant. And the limit of a constant, you know, for any limit of c as n goes to infinity, that's just equal to c. Okay. So this will just be equal to the absolute value of x minus 2. Okay. We want to know what x values will give us convergence. So what you do is say, hey, this thing then will converge when this thing, the x minus 2, the absolute value of the x minus 2 is less than 1. Okay. And so you can expand this into a compound inequality. It's less than 1 greater than negative 1. And then add 2 to all 3 sides. We get 3 greater than 1. And then the radius is just half that interval, right? So 3 minus 1 all over 2 is 2 over 2, which is, the radius is 1? Negative 1, sorry. 3 plus 1 over 2 is 4 over 2, which is 2. So the r value here is 2. So if that's not clear, on the number line, you're going from negative 1 to 3. Negative 1, 0, 1, 2, 3. The r value is always half. It's almost as if you're thinking in 3 dimensions. You would be thinking in terms of like a circle, but the radius is just going to be half of that. Okay, so the full distance, of course, is 1, 2, 3, 4 units, but the radius we think of as like half of it. Okay, so 4 divided by 2 gives you 2, and that will be telling us where this thing's convergent. And literally now you can plug that into your summation up there. So our summation, if you look above, x minus 2, right? So it'd be 3 times, you could use any x value in this interval and it'll be convergent. So say, for instance, 2, right? So 2, well, clearly that's going to be convergent because it'll equal 0, but any other one other than that. So let's say, 0 minus 2. Oops, I'm writing in black. 0 minus 2 to the n. So this would be the sum of 3 times negative 2 to the, well, that doesn't seem right either, but 0 in there, minus 2 to the n. Oh, no. This is plus 1. So sorry. So the radius is 1. I was right the first time. Sorry. I got a lot of stuff on my mind right now. Sorry. Yeah, 1, 2, 3. The radius is 1. Okay. So you basically just take the endpoints, subtract them, divide by 2. So we get 2 over 2 is 1. This is the least important part of the entire book. I'm spending a half hour on it. Okay, so you can take any value in between 1 and 3, for example, 1.5, and you'd have the sum of 3 times, let's say, 1.5 minus 2 to the n, and that would be the sum of 3 times negative 1/2 to the n. And clearly this is convergent because it's geometric. This is geo. Absolute value of r is 1/2. It's less than 1, which means it's convergent. Okay, but you can do that for any value in between 1 and 3, and it'll be convergent. The endpoints we don't know. We'll worry about that in a little bit, but for any other point in that open interval, you're good to go. Okay, let's look at the last kind of version. So we looked at one where nothing is basically convergent except the center. The second one, there's an interval of convergence. The third one, it'll be infinitely convergent. And we have the summation -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. And we're going from n equals 0 to infinity. Okay. Okay, so let's go ahead then and do our ratio test on this guy. So we have the limit as n goes to infinity of the absolute value. And for the absolute value, again, you can kind of just kick out the -1 junk. So you're not going to have to put for a sub n plus 1, you're not going to have to put -1 to the n plus 1 in here. That's silly. Okay, the absolute value will take care of it. So you're just putting n plus 1 in for n wherever you see it everywhere else. So you have 2 to the n plus 1 all over 2 times n plus 1 factorial divided by, in other words, multiplied by the reciprocal of a sub n, which will be 2n plus 1 factorial all over x to the 2n plus 1. Okay, so this will be then the limit as n goes to infinity of the absolute value of x to the 2n plus 2 plus 1 is 2n plus 3 all over 2n plus 3 factorial times 2n plus 1 factorial all over x to the 2n plus 1. Okay. I'm going to rewrite that factorial and write the fractions. So I have 2n plus 1 factorial all over the 2n plus 3 factorial, right? Using the recursive definition for factorial, I could rewrite that as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Okay. And then that will be times x to the 2n plus 3 minus 2n plus 1. Okay. So then that'll equal the limit as n goes to infinity of the absolute value of 1 all over 2n plus 3 times 2n plus 2 times x to the 2n plus 3. What is this going to be? Minus 2n minus 1, so that would just be x squared. You can factor out the x squared part. You don't need to bring around the absolute values because x squared is positive, so it would be silly to write it like that, but I'll write it like that anyways. And this will just be x going to infinity of 1 all n going to infinity rather of 2n plus 3 times 2n plus 2, and then this will equal x squared times well, what is that thing? Well, that's just an L over infinity type, right? So that'll be x squared times 0, and for any x you put in there, anything times 0 is 0. So you can just say, well, that's equal to 0. Okay. So our ratio test says that if r is less than 1, then it's absolutely convergent. And that's the thing that we're working with here. This is our r value. Okay, and our r value is 0, which is definitely less than 1. In other words, for all x, the series converges. Okay, so the r value in this case is then going to be infinity. Okay. Going back to the second example, we have an interval, and we kind of said r less than 1. So what about when r is equal to 1? What happened in the ratio test in those cases, right? When r is equal to 1, the test is inconclusive. So in other words, sure, we found when it was less than 1, but if you consider when it's equal to 1, in other words, when it's less than or equal to 1 or greater than or equal to 1, less than or equal to 3, greater than or equal to 3, we know in the open interval from 1 to 3 it's convergent. But we don't really know about the endpoints because that's where the r value would equal 1. Okay, and in those cases, then the ratio test doesn't tell us anything. So the deal will be you have to then go back to all of those tests from 9.1 to 9.6 and check the series at the endpoints. Okay, so this is section 3. We have endpoint convergence, and we must check these endpoints separately. And you use the test from 9.2 to 9.6. So you're using the comparison test, the nth term test, the alternating series test. Is it geometric? Is it telescoping, etc.? Okay, so let's try one of these. Let's look at example. The example from above where we had the summation 3 times x, stupid pen games on, 3 times x minus, was it 2 to the n from n equals, I believe it was 0 to infinity. And we determined that the sort of radius of convergence was 1. And in fact, it's convergent on the interval from 1 to 3. Okay. Okay, so we need to check the endpoints. We need to check x equals 1 and x equals 3 to see what happens. So how do I do this? Well, you're just going to substitute the value 1 into the original series and then use your series test. So we have 3 times 1 minus 2 to the n from n equals 0 to infinity. This will be the sum from n equals 0 to infinity of, so this will equal 3 times negative 1 to the n. This thing is geometric. This is a geometric What type of geometric? It's R value, absolute value of R is absolute value of -1. The A value is 3. We don't need that though. Absolute value of -1 is 1, which is not less than 1, which means it's divergent. Okay, then we go to the other endpoint, is 3. And this time we just plug that into the summation, so we get the sum from n equals 0 to infinity of 3 times 3 minus 2 to the n. Okay. That'll equal the sum from n equals 0 to infinity of 3 times 1 to the n. And again, that's a geometric, right? That's just geometric with the absolute value of r equaling the absolute value of 1, which equals 1, which is not less than 1, so it's divergent. Okay, and you have to do that if I give you on a test and you're checking the endpoints, you have to plug it in and then tell me, you know, what kind of series is it? Then is it divergent or divergent? Is it divergent or convergent, and why? Okay, you can't just sort of guess. Okay, that's not gonna, you're gonna lose points if you guess. Okay, so anyways, at the end of the day, it's divergent at both endpoints. So the interval of convergence, it's only convergent on 1 to 3. If it had converged at the endpoints, then you would put in the square bracket on that particular endpoint. Okay, so anyways, this is called officially then the interval of convergence. Okay. Okay. Let's move on to another one. And see what happens. So the example, sum of x to the n all over n from n equals 1 to infinity. Okay. This guy is going to clearly be divergent at 1 when x is 1, because why? Well, it'll be related to it will be the harmonic series, and the harmonic series is divergent. So we know it's going to have some divergence. It's not going to be all real numbers, or r equals infinity. Let's take a closer look, right? So the r is the limit of the absolute value of x to the n plus 1 all over n plus 1 times n all over x to the n as n goes to infinity. This will equal the limit as n goes to infinity of, let's rearrange a little bit, n over n plus 1 times x to the n plus 1 over x to the n. That'll be x to the n plus 1 minus n, which should just be x. Okay. And then we could factor out the absolute value of x, and we're left with the limit of n over n plus 1, which we could just look at and know that goes to 1, I hope. Right? You just circle it as n over n is 1, the limit of 1 is 1. So this will equal the absolute value of x. We know then that this series will converge when the absolute value of x is less than 1 because of the ratio test. In other words, when x is less than 1 but greater than -1. And so from here, the radius of convergence, if you just cut the interval in half, will be 1. And then we need to check the endpoints, -1 and 1. Okay. So at x equals -1, I'm going to plug that into my original series. So I have the series -1 to the n all over n from n equals 1 to infinity. This is an alternating series. So try alternating series test. So first, you take the limit of the term, the a sub n portion of the terms of the series. Limit of 1 over n is just going to be 0. So n goes to infinity. So far, so good. Then I need to show it's decreasing. So I'll do a ratio test for monotonicity. In other words, look at a sub n plus 1 over a sub n. That will be 1 over n plus 1, all over 1 over n. Multiplying by reciprocal will be n over 1. And of course, that will just be n over n plus 1, which we know will be less than 1 for n greater than 1. Okay. So that proves it's decreasing, and the limit goes to 0, so therefore it's convergent. Okay. And you need to show that. Okay. You can't just say, oh, this is convergent. I know it is. No. Try x is 1. So this time I'm plugging 1 in for x into the original series. And this is a case I sort of said already. So this series n equals 1 to infinity of 1 to the n over n. 1 to any power is 1. So I could replace 1 to the n with just 1, right? And then what is that? Well, hey, I already know what that is. That's the divergent harmonic series. So I write that down. That's the harmonic series. And we all know this one is divergent. So there's no reason to have to do some sort of weird proof. It's P series, P equals 1, divergent, if you would rather. Okay. So then ultimately the interval of convergence, where this thing converges, it'll converge at the left end point, -1, and then all the way up to 1, but not including 1. Okay, so that would be kind of your official answer that they're after at the end of the day. Okay, so the series would be useful on that interval if it was, in fact, the limit of a sequence of polynomials. You'd only be able to use it there. Okay, let's look at one more and then we'll hit another topic. So this example, sum of -1 to the n times x plus 1 to the n all over 2 to the n from n equals 0 to infinity. This is the video quiz, folks. I know I've been forgetting to put them in lately. I'm sorry. Okay, I always forget. These sections are kind of difficult, and I forget. Okay, so video quiz, video quiz, video quiz, video quiz, video quiz. And this is the last problem in homework number 7. Okay, so this is homework number 7, question 4. Okay, so first we do the, we're going to have to find the radius, so we get our r value, so we're taking the limit of the absolute value. Again, you don't need that -1 thing. The absolute values take care of it. So you get x plus 1 to the n plus 1 all over 2 to the n plus 1 times the reciprocal of a sub n, which is 2 to the n all over x plus 1 to the n. Okay. We can simplify that material. 2 to the n over 2 to the n plus 1 is 1 all over 2. And then times just x plus 1 to the first power. Subtracting exponents, n plus 1 minus n is just 1. Then you can factor out the x plus 1. Well, that's all a constant, right? There's, again, the n, the limit is dependent on n. It's going, n is to infinity, so this thing is just a constant. In other words, the limit of that thing is just the absolute value of 1/2 times x plus 1. Okay. And then we'll know it's convergent whenever that thing is less than 1, so we can then wedge the 1/2 x plus 1 in between 1 and -1. And then we're going to multiply through by 2. So I'll have -2 less than x plus 1 less than 2. And then subtract 1 from all three sides, and you get -3, and then less than 1 over here. Okay, so it's definitely convergent in that interval. So we have what? -3, -2, -1, 0, 1. The radius is half that interval, so it's just 2. We need to figure out the interval of convergence, though. So we need to actually zoom in on -3 and at 1. So I take -3 and I dunk it into my original summation. So I have -1 to the n times -3 plus 1 to the n all over 2 to the n. And then I can simplify a little bit. So this is the sum of -1 to the n times -2 to the n all over 2 to the n. Okay. And then you could rewrite this as a sum of -1 to the n times, well, what is -2 to the n? It's really the same as -1 times 2, all raised to the nth power. And then if you have like a product to a power rule, right? So a times b to the n is a to the n times b to the n, right? Just writing that in, that factoid there at the top left. So I get the, and it's all over 2 to the n. So I get the sum of -1 to the n times -1 to the n again times 2 to the n, which is nice because then the 2 to the n's cancel. And then I can use the other exponent rule, right? So if you have a to the x times a to the y, that's just equal to a to the x plus y. So in this case, I have the sum of -1 to the n plus n, which is 2n. Then -1 to the 2n is the same as -1 squared to the n. -1 squared is 1. 1 to any power is just 1, so I could replace 1 to the n with 1, because it's always equal to 1. So this will just be the sum of 1. You could say that's a geometric and with r value equal to 1, so not convergent. But let's try the nth term test. Okay, so note nth term test, where you take the limit of the a sub n portion of the series, and the a sub n portion here is just a constant. The limit as n goes to infinity of 1 is just equal to 1. The nth term test says if that's not equal to 0, then it's divergent. So we just found the limit was not equal to 0, hence it's divergent. Okay, so it's a no-go on that left endpoint. Let's try the other endpoint, x equals 1. Okay, so substituting into our series, we get -1 to the n times 1 plus 1 to the n, all over 2 to the n. That equals a series of -1 to the n times 2 to the n, all over 2 to the n. We can then remove the 2 to the n's, and we'll end up with the series of -1 to the n. And again, you could do the nth term test, or you could say it's geometric. Test. The limit as n goes to infinity of -1 to the n, well, that will be -1 if n is even, -1 if n is odd, and then +1 if n is even. Therefore, the positive terms and the negative terms go to different limits. In other words, this thing does not exist. In other words, it does not equal 0. And hence, it's also divergent. Okay, so this guy then just only is going to have convergence. The interval of convergence, or the interval of usefulness, will just be the open interval from -3 to 1. Okay. Okay. The question then kind of becomes, what about the derivatives and integrals of these things? Okay, so once I get like a, sine of x is equal to this power series, and I know sine of x, the power series for sine of x is convergent everywhere, so it's useful everywhere. Can I do calculus on it? Can I take integrals of it? Can I do derivatives of it? Is the interval of convergence going to remain intact? So yes, it turns out that it will kind of, except at the endpoints. Okay, so section 4, you can differentiate and integrate power series without too much of a mess. Okay, so let's look at that occurrence. So let's start with our power series, our generic power series centered at 0. The sum from n equals 0 to infinity of a sub n x to the n, right? We can expand that a little bit, because the expanded version is going to generally be easier to take the derivative and integral of. So, let's take a look at it. So this will be a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x to the 2 plus da da da. Okay. Then let's look at the derivative, right? So p prime of x. And usually the problem with the derivative is the little summation index, the lower limit of the summation. It may change. It doesn't always have to change, but it may change. So anyways, with that in mind, what we do is kind of just take the derivative of a sub n x to the n. A sub n is a constant, so you're just taking the derivative of x to the n, right? So it'll be, bring down the n, and I'm going to put the n in front, so it's n a sub n x to the n minus 1, right? You take derivative, you just subtract 1 from the exponent. Okay. And then when I expand this, it's going to be, and now I'm not using the formula. I'm actually taking the derivative of the terms. Okay, so I'm doing a term-wise differentiation. So the derivative of a sub 0 is just 0. I'm not going to write that. The derivative of a sub 1x is a sub 1, plus the derivative of a sub 2x squared is 2a sub 2x. And we can even do one more. The derivative of a sub 3x cubed is 3a sub 3x squared, and then on, right? So where do I need to start my index? Can I just put 0 again? Well, no. If you put 0, what's going to happen is you'll have a negative exponent on your x value. We don't allow that here in calculus land. You could do that in, well, you can't do it in real calculus. You can do it in a complex calculus, okay? But if you have imaginary numbers, you'll find a way to do that, to have negative exponents. But for us, no. It's a no can do. So the index, or the lower limit, excuse me, will start at 1, right? Because if you put 1 into our blue formula here, it will be 1 a sub 1 x to the 0, which is just a sub 1. You put 2 then in next, 2 a sub 2 x to the 1, and that's what we get. So that works. Okay, the third one then is the integral of the power series. And again, what I'm going to do is kind of just integrate that equation in blue. I'm going to write it in red though. So how does integration work again? Well, we add 1 to the old exponent and then divide by that new exponent. Okay, and again, we're going to worry a little bit about the lower limit value. Okay. So what will this equal if we just did term-wise integration? In other words, take the derivative of that. What would that be? Well, that would be a sub 0x, and then take the derivative of this. What would that be? Well, that would be a sub 1x squared over 2, and then so on, right? So plus a sub 3x cubed over 3, plus a sub 4 x to the 4th over 4, plus da da da. Okay, so what then? What is this? You know, is it 1? Is it 0? Is it 2? You know, there really doesn't seem to be too much of a logic to it. I'm sure if I sat around for a couple hours, I could figure it out, but it doesn't seem to have a lot of logic to it. In this case, it just turns out to be 0 again. Okay. So, you know, if you put in 0, you get a sub 0 x to the 1 all over 1, which is a sub 0 x. If you put in 1, you get a sub 1 x to the 2 all over 2, which is this guy. So it seems to work. Okay. And of course, there's a plus c after everything. Okay. So anyways, the radius of convergence will not change if you do this. So you're kind of safe integrating and differentiating, but you got to be careful about the radius of convergence. Okay, so anyways, let's look at an example, and these problems are kind of long. Basically, you're finding the interval of convergence for the original function and its integral and its derivative. So find the IOCs. Okay. So the original function f of x is just keeping it easy, n equals 1 to infinity of x to the n over n. So I'm going to get all 3 of these first, just right off the bat. So f of x, expanding this thing so we can worry about the lower limit and kind of align everything. What are we going to get? You plug in 1, it'll be 1 to the n over 1, so 1. Plug in 2, you get x squared over 2. Whoops, the first one will be x, right? X to the 1 is x, not 1. Plus n equals 3 is x cubed over 3, plus x to the 4th over 4, etc. Okay. Then our derivative. And again, we have to worry a little bit about that lower limit there. So bring down the n this time. So it would be n x to the n minus 1 all over n. Let's simplify that. So n equals something to infinity of just plain old x to the n minus 1, right? Then I kind of look at the derivatives term-wise. So I'm not expanding the summation. I'm just taking the derivatives of these guys and writing them down. Okay. So what's that going to be? That'll be 1 plus 2x over 2, which is x, plus 3x squared over 3, which is x squared, plus 4x to the 4 over 4. So pretty much the most standard polynomial in the universe. Okay. And then let's take, oh, whoops, I need to figure out the indices. So it looks like if I plug in 0, it's not going to work because I'll get a negative exponent. So it must be 1 then, I think, right? So if you plug in 1, you'll get x to the 1 minus 1, which is x to the 0, which is 1. Plug in 2, x to the 2 minus 1, which is x to the 1. So that seems to work. Okay. Finally, we'll look at the integral of f of x. Okay, so what I'm doing is integrating the terms, basically. So the formula then will be xn plus 1, and then you divide by that, so it'd be n plus 1 times n. Again, I'm very worried about this lower limit. Let's just go ahead and integrate term by term. So the first term will be x squared over 2. All right, the integral of x is x squared over 2, plus x cubed all over 3 times 2, plus x to the 4th all over 4 times 3, plus x, and it's better not to multiply these out. I think I might have said that before, but it's better for pattern recognition not to multiply it. So instead of 6, write 3 times 2. Instead of 4 times 3, which is 12, instead of writing 12, write 4 times 3, etc. Okay, so where does this lower limit start? So if I plug in 0, that's not going to work because the first exponent would be 1, so I'm probably 1, right? So if you put in 1 for n, x to the 1 plus 1 is 2. All over 2 times 1 is 2. Plug in 2, I get x cubed. All over 3 times 2, yeah, that works. Okay, and then plus c. So you still have to worry about the plus c stuff. Okay. Okay. Anyways, then go and get the interval of convergences. Okay, so let's start with f of x. So our f of x was the series x to the n all over n from n equals 0, or 1 rather, to infinity. Do the ratio test, so the limit of the absolute value of x to the n plus 1 all over n plus 1 times n all over x to the n. That will be the limit of, did I give you the video quiz? I'm hoping I gave you the video quiz. The last question was the video quiz. Did I make that clear? Yeah, I wrote it down. That was the video quiz. Okay. Anyways, this guy then would be the absolute value of x to the n plus 1 minus n is x to the 1. So we have x times n over n plus 1. You can factor out the x. You have to bring the absolute value along for the ride. And then you're just looking at the limit of n over n plus 1. And of course, that's just the limit of 1. So that it will equal the absolute value of x. So this will be convergent, and all of them will be convergent. The f of x, derivative of f of x, and the integral of f of x will all be convergent in between 1 and negative 1. So they all have the same radius of convergence, which in this case is 1. We'll just have to check the endpoints for all of them. So you basically have 6 sort of convergence tests to do. So let's look at the first one, plugging in negative 1, so x is negative 1. So negative 1 to the n all over n. This looks like alternating series, so try alternating series test. We have the limit of the a sub n portion is 0, and then do the ratio test for monotonicity. 1 all over n plus 1 divided by 1 over n. It's going to be n over n plus 1, which of course is less than 1. So it's convergent. And then try x is 1. And of course, that'll be the harmonic series. The harmonic series is divergent. Peoples. Okay, so the interval of convergence for f of x, is going to be including -1, but not including +1. Okay, let's look at f prime of x, which of course was the sum from n equals 1 to infinity of x to the n minus 1. We don't need to go through the ratio test again, right? Because, as I said, the interval of convergence, the radius of convergence will not change. It's only those endpoints. So all we have to do is kind of check it at x equals -1, and then over at x equals +1. Okay. So we have then the first guy, the sum of -1 to the n minus 1 from n equals 1 to infinity. This is just, it doesn't look like it, but it's geometric. Okay. So it's geo with the absolute value of r equaling 1, which is not less than 1, so it's divergent. And likewise for this guy, right? The r value is just 1. N equals 1 to infinity. So geo, absolute value of r equals 1, which is not less than 1, so it's divergent. Okay, I'm a little hesitant to call these geo because they don't necessarily have the same form that we gave you in the book, right? In our form, it was always n equals 0 to infinity of ar to the n, right? So are these the same? You could always do kind of a substitution, and even if they aren't the same, deleting one or two terms from the series will not affect the overall convergence or divergence. So, but anyways, you can kind of morph these things, I believe, by doing a substitution on the lower limit. So you could rewrite the lower limit by saying j equals n minus 1. So n, in this case, would equal j plus 1, right? So you would get j plus 1 equals 1 to infinity of 1 to the n is j plus 1 minus 1. And then that would equal the sum from j, if you just subtract 1 from both sides, right? You get j equals 0 to infinity of 1 to the jth power, which now is in the form, if you just, that's a dummy variable, so you just put it back into terms of n, 1 to the nth power. And now it's clear it's a geo with radius 1, a values 1, and it's divergent. Okay. You don't have to do that. It's just maybe in differential equations, if you end up working with series all day long, that kind of stuff is helpful. So anyways, the second function, the derivative, its interval of convergence is from -1 to 1, not including the endpoints. Okay. Finally, then the integral of f of x dx, which we saw to be the series from n equals 1 to infinity of x to the n plus 1 all over n times n plus 1 plus c. Again, we don't have to do the ratio test. We just need to plug in the endpoints. The plus c portion won't affect the overall convergence or divergence of the series, so you can kind of neglect that. But let's take a look at the endpoints. So what do we have? -1 and 1, right? So plugging in -1, we get the sum of -1 to the n plus 1, let me box this, all over n times n plus 1. And this guy is alternating. Okay, so try the alternating series test. And what do we get? Well, the limit, first off, we look at the limit, right? So the limit of 1 all over n times n plus 1 will equal 0. Secondly, the ratio. Okay, so 1 all over n plus 1 times n plus 1 plus 1, which is n plus 2, times the reciprocal of a sub n, which is n times n plus 1 all over 2. That will equal, whoops, all over 1. Sorry. Over 1. If I get my pen to work someday, that would be great. There it goes. So I end up with n squared plus n all over n squared plus 3n plus 2, and I'm comparing that to 1, and of course that thing is definitely less than 1. Okay, so this guy is convergent on that endpoint. Let's look at the other endpoint, x equals 1. So we have the sum of 1 to the n plus 1 all over n times n plus 1. 1 to any power is 1, so you get the sum of 1 all over n times n plus 1. This time let's do a limit comparison test. So note limit comparison. Looks like you could probably do a telescoping on it, but limit comparison really is a little faster. So note limit comparison test. What are we comparing with? So compare with the series, and what we're going to do is just kind of look at the first part of it, right? So the series of 1 over n squared, which is what? Well, it's a p series. P is 2, and it's convergent. So secondly, do the limit, which is the ratio of the terms of these two series. So it'll be the limit of 1 all over, and let's go ahead and distribute this n. So it'd be n squared plus n all over 1 over n squared as n goes to infinity. That will be the limit as n goes to infinity of n squared all over n squared plus n. Okay, and then limit of n squared over n squared is just the limit of 1, basically at the end of the day, which will equal 1. And the criteria for the limit comparison test has to be greater than 0 and finite. And if that's true, then both series have the same behavior, so the series also converges. Okay, a lot of work. Okay, ultimately then at the end, our interval of convergence is the closed interval from -1 to 1. Don't try to find rhyme or reason in these endpoints. Sometimes they can be open, sometimes they can be closed. You have to do the grunt work. Okay, there's not going to be any pattern finding for us because we don't have time to look at it in that detail. We need to know how to do these kind of methods. Okay. Okay, so on a test, you would have to do that whole spiel. You have to test the endpoints. You have to plug in the endpoints, simplify the series, do some sort of convergence test, and make your conclusion. Okay. Okay, we'll leave it at that for now, and we'll see you next time.